Greetings and welcome. In this session, we will discuss about the shear stress and velocity distribution for steady and laminar flow through pipe. In the last video session, we have discussed about the entrance region theory, which was the first session of the module internal flow. In that, we have seen about the hydrodynamic entrance region and fully developed region of the flow through a pipe. So with the help of that theoretical idea, here we are going to see a mathematical expression for shear stress and velocity distribution for steady and laminar flow through pipe. In order to study expression for these two, we have some assumptions. These are: flow is a one-dimensional, that is a flow in the direction of a flow, that is x direction. Second, flow is a steady, that is there is a no change in a viscosity with respect to time at a point. Then flow is a laminar, means the flow is a flowing with a different layers. These layers are not crossing each other. These layers are moving in a parallel to each other. So such flow is called as laminar flow. Fluid is a viscous, which is used here. That is what viscosity, that fluid is having viscosity, that is a real fluid. There is a no slip condition at the pipe surface. So we have discussed about this in a last video session. No slip condition means what? Because of viscosity of the fluid property, the fluid particles which are othering at the pipe surface, they have zero velocity, means these are not moving, they are stuck to the surface. Such phenomenon is called as no slip condition. And last is a pipe, considered here as a horizontal pipe. Now for this expression, we here use this diagram. So in this diagram, we have considered a circular pipe of radius capital R, which is with the flow of fluid. In that, a small fluid cylindrical element is considered with a radius small r, and the length of that fluid element is a dx. Then this fluid element is at a distance from the pipe surface, that is a y. So y is equal to capital R minus small r. So y is a distance between the fluid lateral surface and pipe inner surface. Then here we consider two sections. Section 1 we consider at a distance of x1 from the left side, and section 2 we consider at a distance of x2 from the left side. Thus, length of a pipe considered for the study as a L is equal to x2 minus x1. Now in this diagram, we consider forces which are acting on the fluid element. Now as per the discussion in a fluid dynamics module, that is in the fluid dynamics, we consider Euler's equation, where the forces acting on the fluid element are pressure forces and shear forces. So here are two forces which are acting. These are shown here. Pressure force is acting on the fluid element perpendicular to the cross-sectional area of the fluid element, and shear force is acting on the surface of the fluid element. That is why it is shown on the both sides. Let us discuss about these two, pressure force and shear force, in a further slide. Now pressure force, we will consider here cross-sectional area of the pipe. So this is a area. This area is a elemental area, that is dA. So force acting here, that is perpendicular to this area. So intensity of pressure is a P. So force is pressure into area. Thus P intensity of pressure and area will be here pi r square. pi r square. So that is what force acting on the forward direction on the left side of the fluid element. Similarly, on the right side of the fluid element, the force is acting in opposite direction. That is what P, intensity of pressure, plus this is a change in a pressure, delta P by delta X, that is a pressure gradient, into dx into area. So this whole is a change in a pressure intensity in the bracket multiplied by area, that is cross-sectional area. Now the direction of this is in opposite direction, because as the fluid is provided here or considered here is incompressible. So that is why in this case it is under compression. So in the compression, there the forces in a forward direction and in a backward direction, these are opposite to each other. So this is what pressure force in other side of the fluid element. Now about the lateral surface of the fluid element, that we will see. So here this fluid element is shown. So fluid element is like this in a two-dimensional view or 2D diagram. Fluid element is like this, and if you consider three-dimensional, then this will be this, like this. So this lateral surface, what we are going to consider. So this lateral surface will be what area, lateral surface area will be what circumference of this circle, that is 2 pi r circumference multiplied by this distance, that is dx. So lateral surface area will be what 2 pi r dx. This is the surface area of the fluid element. Multiplied by shear stress, that will be what shear force. So shear force will be equal to what tau into 2 pi r dx. So in this way we have discussed about the forces. Now about the sign convention we will use here. These all forces we write with the help of equation, that is by Newton's second law of motion. We say that summation of all forces is equal to 0. In this case, for the forces in forward direction we use positive sign, for the forces in backward direction we use a negative sign. So here pressure forces, this force is a positive because it is in forward direction, and other forces, second force, it is in backward direction, and also shear force which is acting, that is on the element, that is in the opposite way. So opposite to the direction of flow. So that is why it is having also negative sign. So putting these forces, first P pi r square, this force, minus this second force here with minus sign, already we discussed because it is backward, and third force, that is a shear force, tau into 2 pi r dx with the minus sign, because again it is in opposite direction to the flow. Now solving this bracket, we find P pi r square, this term as it is, this P into pi r square comes here with minus sign, this minus sign along with delta P by delta X, that is a pressure gradient, into dx multiplied by this term P pi r square minus tau into 2 pi r dx as it is equal to 0. Here we find these two terms same because these are having plus sign, minus sign, they get cancelled. Rest of the terms we write here. Observing this, we find that on the both side dx same, get cancelled, pi term get cancelled, r square in that square and this r get cancelled. Whatever remains, that we write. While writing, we take tau on the right side. This 2, if we bring on the left side, it comes at the denominator. So that is why equation becomes minus delta P by delta X into R by 2. This is what shear stress. We say this as equation number 1. Now here in this case, minus sign we consider for the pressure gradient, because in the flow, as the flow is flowing, there is a friction which is taking place between the layers of the fluid flow. So because of that, pressure decreases in the direction of flow. So that is why pressure gradient is a negative. So that is why here minus sign we consider for that. Now this tau is equal to minus r by 2 into delta p by delta x. This equation number 1 we use to obtain shear stress distribution. So we have two parts of this video. First part is a shear stress distribution and second part is a velocity distribution. First part, shear stress distribution, for that mathematical statements whatever we have written here. Now we will see shear stress distribution, how to obtain. For that we use this equation 1 and we apply the boundary conditions. Now boundary conditions we will see. Here are two boundary conditions. One is at the center of the pipeline, that is at the radius 0. We put in the equation number 1, that was tau is equal to minus r by 2 into pressure gradient. Here putting r is equal to 0, we find whole expression as a 0. So at the center means at radius equal to 0, we find the shear stress 0, that is shown here. Then at the wall surface means at the pipe surface, small r is equal to capital R. Here we use shear stress maximum, we put tau is equal to tau max. So putting both these in the equation 1, we find tau max equal to this capital R by 2 into pressure gradient. We say this is the equation number 2. Now, if you observe the diagram, we find maximum shear stress at the wall surface and 0 shear stress at the center of the fluid flow. So here we find that shear stress is varying from the center 0 to maximum towards the pipe surface on the both sides. So here this diagram is called as shear stress distribution, and nature of this shear stress distribution is a linear, that is a straight line. Now we will go to the velocity distribution. That is the second part of the video. In this we know that this is a pipe with radius capital R. This is a fluid element with small r radius. Distance of this fluid element from the pipe surface is a y, which is again capital R minus small r. Here by Newton's law of viscosity we have tau is equal to, means shear stress is equal to mu, that is a dynamic viscosity, into d upon dy, that is a velocity gradient. Here this dy, that is a distance between the layers dy. For that we use now y is equal to capital R minus small r. Here we differentiate this equation, we get dy, derivative of this y, left side, capital R, that is a radius of a pipe, which is a constant. Maximum radius is capital R, which is a constant. Derivative of constant is 0 and derivative of small r is a dr. So we find dy is equal to minus dr. Substitute this dy is equal to minus dr in this Newton's law of viscosity. We get equation tau is equal to mu into du upon dr, that minus sign we give at the place of mu. This equation we say as a equation number 3. Now for the velocity distribution we compare equation number 1 and equation number 3. Equation number 1 that we will see. So equation number 1, left side is a shear stress, right side is a minus r by 2 into delta p by delta x. And equation number 3 has a left side shear stress and right side is written. Means equation 1 and 3, left side is a shear stress, so it is the same in both. That is why we can equate right hand side of the equation 1 and 3. So we have written this right hand side of the equation 3 here, that is minus mu into du upon dr is equal to, from the equation 1 right hand side of the equation, that is minus r by 2 into pressure gradient. This equation we arrange in the form of du, that is a change in velocity. This minus sign is on both sides, it get vanish. Dr comes on the right side of the equation, and this mu comes at the denominator on the right side of the equation. So equation becomes du is equal to r divided by 2 mu into delta p by delta x into dr. This is the equation for change in velocity. Now this is in differential form. In order to get velocity equation, we have to integrate this equation. So integrating this equation, integration of left side integration du is equal to integration of right side integration. Here we write, while writing we take this r along with dr for the integration purpose. Now here 1 upon 2 mu and pressure gradient, we consider these two expressions as a constant, that is why they come out of the integration sign. And here integration of r into dr remains. Integration of du is a u, that is a velocity. Integration of r is a r square by 2 plus c. This is called as constant of integration. This equation is equation number 4. Now we have to obtain expression for this c, that is integration constant. To obtain it, we use boundary conditions. So at the wall surface, we know that small r is equal to capital R, and at the wall surface, because of no slip condition, there is a no velocity of the fluid particle, which u is equal to 0. So putting these values, r is equal to capital R and u is equal to 0 in the equation number 4, we find 0 left side, right side 1 upon 2 mu into pressure gradient as it is, into at the place of small r we use capital R square by 2 plus c. Arranging the equation in the form of c, on one side these all terms we take another side, that is why minus sign comes. Again here we take this 2 mu into 2, that becomes 4 mu. So c is equal to, we get expression minus 1 by 4 mu into pressure gradient into capital R square. Substitute this c expression in the expression 4. Again in expression 4 we write this 2 mu into 2 together, that is 4 mu. So 1 upon 4 mu into pressure gradient into small r square minus expression for the c, this along with minus sign. So in this expression we can take 1 by 4 mu delta p by delta x. These two terms we can take common, but while taking we take first this term as a common with minus sign. So we find here small u is equal to minus 1 by 4 mu into pressure gradient into capital R square minus small r square. As we took this term along with minus sign, that is why if we find the expression in the form of larger radius minus smaller radius. Capital R square is a full radius and small r square is a small radius of the fluid element. So this is the relation for local velocity u. Now as we know, at the center r is equal to 0, velocity is a maximum. That is why putting these r is equal to 0 and u is equal to u max in the equation 5, we find u for that u max minus 1 by 4 mu into pressure gradient as it is. Here r square minus small r value 0, that is why it will be vanished. So we get this expression, say equation number 6. This is a relation for maximum velocity at the center line of the pipe. Then we compare the equation. For that we rearrange this equation number 5. In this arrangement we do u is equal to minus 1 by 4 mu delta p by delta x into r square. R square we take common from this bracket. In the bracket, what remains? Minus 1. 1 minus small r square by capital R square. So here, if you observe this covered portion is nothing but U max. So for this covered expression, we use U max. So we find the equation U is equal to U max multiplied by this rest bracket as it is. We say this as equation number 7. So this is the relation between local velocity and maximum velocity. Now we will write or we show here the diagram, that is variation of velocity with respect to radius. As at the surface, means capital R, no slip condition, velocity is 0. At the center, R is equal to 0. Here, shear stress is a 0. Thus, velocity is maximum. Means your velocity varies from the pipe surface from 0 value to maximum value toward the center line of the fluid flow. Thus, this is the curve which is shown. It is a velocity distribution profile, which is parabolic in nature. It is like a parabola. That is why we say velocity distribution profile for the flow through pipe is a parabolic in nature. So in this way, we have studied the expression for shear stress distribution and velocity distribution for a flow that is one-dimensional, steady, laminar and of viscous fluid in a pipe or through a pipe, that is the internal flow. Let us meet in the next video session. Thank you.